Okay, good afternoon. So I hope so far everything is okay. And any questions? So last time we talked about this time correlation function, and later on actually we will use repeatedly this idea or this tool in our derivation calculations of quantum dynamics and spectroscopy in condensed matter, or condensed phase, sorry, in condensed phase molecular systems. And today we're going to talk about a specific model or a specific problem. Already the fifth lecture is already the second half of this short course already. So we begin to explore various specific systems or specific problems. And one problem that we concern a lot, especially in our research group, is about excitation energy transfer or charge transfer. I will talk about both stuff because they are related to each other. Yeah. So excitation energy transfer, and charge transfer. I'm not going to talk explicitly about charge transfer. This will be kind of in the background. I'll mention, okay, this can be bring to attack the same or similar problem in charge transfer, but I'll focus mainly on electron energy transfer, excitation energy transfer over molecular systems. But this is in the background because they can more or less described by the same model, although some details could be different. So for this, I will introduce so-called exciton, Hamiltonian. Define our problem. Okay. And then talk about the coupling or driving force couplings. Normally you will see people say energy transfer, excitation, energy transfer, so ET. Or charge transfer, CT. And then I'll explicitly derive so-called Redfield theory. So in the last lecture, we derived, actually already 2 lectures before, we derived the quantum mass equation for electronic system coupled to a bunch of environments, system-based coupling, under system-based coupling model. We didn't explicitly specify the Hamiltonian or the problem. Here I'm going to derive this within this model. Okay? So the equations of motion that we derived previously is actually kind of a formal expression, formal equation of motion. In order to make it useful, or in order to use that equation of motion, you need to actually specify the Hamiltonian and the explicit form of a system-based couplings. Okay? And that depends on the problem that you want to solve. And regarding energy transfer or charge transfer problem, the end result of the equation of motion are very similar. Right? I call it the Redfield theory because that equation of motion was derived based on the assumption that the system-based coupling is small. Okay, we call this the Redfield regime of our of the quantum dynamics. Okay. So we concern about a so-called multi-chromophoric system. So a system with a collection of chromophores. Here, chromophore normally refers to a molecule, but it's not necessarily so. You can say it could be a quantum dot. Okay, it could be some defects in a solid-state system. Titanium ion in your crystal, things like that. Okay, the same. Multichromophoric means we are dealing with a bunch of chromophores arranged in a specific geometry. Normally, can be aggregates of molecules or some arranged lattice points, like that. The simplest one will be a system with, well, a donor and acceptor. Okay. So instead of doing general multichromophoric equations, here we will mainly focus on a simplest one. In that case, we consider only two chromophores. Okay. One I'll call it donor. The other one I'll call it acceptor. When we consider the donor and acceptor, or if we just extend this idea, if we consider these molecules an individual molecule in a multichromophoric system, this is a mono within your system. Excitations or any states that we refer to as the monomeric state, monomeric subsystem in this total system is usually called a site. So this will be a site. This is just some terminology. So donor is a site for multichromophore. For a system with more than two chromophores, then of course it's not just donor and acceptor. Donor can be a group, a bunch of sites. Okay. And we'll usually label it as 1, 2, 3. So it's site 1, site 2 as your donor and acceptor, so on and so forth. Okay. But that's just terminology. Here we have a distinction of donor and acceptor. Normally, the distinction is on its energy. Donor has a high energy state, and acceptor has a low energy state. So by nature of energy equilibrium, the excitation on the donor state will tend to transfer or go into the acceptor state. Okay, the system tends to going from a high energy state to a low energy state. This applies to energy or charge. If you put an electron on the donor, electron donor, and this will be an electron acceptor. I didn't specify its energy or electron or whatever. Okay, proton donor, proton acceptor, the same model. Okay. Yeah. So we want to consider system like you have a donor, have one electron, acceptor without electron, and donor acceptor with one electron. This will be electron transfer. If you concern excited state on donor, became excited energy, excited state on acceptor. This will be excitation. Many other models falls into this category. And what we refer here is localized transfer model, meaning excitation is allocated on the donor and only on the donor, and then going to acceptor. And so this assures that excitation on this molecule and the excitation on this molecule are separatable. But in many systems, when these couplings are strong enough, then this excitation could be delocalized on both molecules. Okay, and actually the Redfield theory, Redfield regime that we are going to describe refers to this regime of dynamics. in order for this to happen, then your donor and the acceptor has to have some sort of a coupling. We mentioned this when we derive the Fermi-Golden's rule. Okay, electronic coupling is a must if you want to have quantum transition from one state to another state. They must couple to each other. So those two systems will have a coupling. And each individual excitation will have some sort of excitation energy. Okay. So for each molecule, you will have a ground state of the molecule and some excited state. In this case, it will be a state with one electron. Okay. In the molecule. And we consider this case excitation energy transfer. In that case, we refer to ground state of one molecule and some excited state of the molecule. Because it's a donor, we will write I want to make sure that I have a consistent notation. So in general, I call this psi 1, this psi 2. So we have a ground state psi 1, excited state psi 1, ground state psi 2, and excited state psi 2. To describe this process, we actually normally we utilized a model called the Frenkel exciton model. It's excitation, so it's some sort of exciton. Actually, in condensed phase physics, exciton refers to electron-hole pair. Okay, and in a molecular system, whenever the system is excited, then you create a hole on the molecule, meaning you have some transition from some field molecular orbital to some from electron transition from occupied molecular orbital to an unoccupied molecular orbital. So you create a hole at the occupied orbital. For example, your HOMO, your highest occupied molecular orbital, and then create an electron at the unoccupied molecular orbital. For example, your lowest unoccupied molecular orbital, LUMO, right? And usually, normal HOMO-LUMO transition is the lowest energy transition in a molecular system. So you have a hole on HOMO, and an electron on LUMO, and this hole and electron actually are on the same molecule, on the same site. Okay, so they are tightly binding to each other. They are close to each other, basically on the same molecule. Okay, this is called Frenkel exciton. Frenkel exciton. Usually, very often, it's also called a tight binding molecule. It's tight binding because its electron and the hole has similar spatial distribution. Okay, they locate on the same position in space. Tight binding. There's a good some useful numbers or thinking from this. Okay, in normal inorganic systems, you can also create excitons in there. For example, you can create exciton in silicon crystal. Okay? But the normal electron-hole binding energy in such system is in the range of a few or 0.something milli electron volt. Very small, much smaller than thermal energy. So in that case, your electron and hole, electron has a negative charge, hole has a positive charge. So naturally, they bind to each other. They are close to each other. But in those inorganic systems, like in silicon, the screening of the environment is very strong, making this interaction very small. So they dissociate, they go to different direction. Electron hole separates easily in such inorganic systems. However, in molecular systems, very often for normal organic dye, this electron hole binding energy is in the range of a few point something, 0.5 electron volt, much higher than the thermal energy, meaning it actually bind to each other strongly, okay, and requires additional drive force to separate electron and hole, okay, and that's why in organic materials you always need to have a hole conducting material and the electron conducting material. Put them together. At least you need to have some sort of double layer structure. And electron hole separation only happens at the interface. Okay. You need to have this driving force of electron affinity higher material to grab your electron in order to separate your electron in your hole. Okay? That's why we need that kind of architecture for organic photovoltaics or organic light emitting diodes. Now let's go back here. So in the Frenkel exciton model, we only consider the ground state and excited state of any chromophore. Effectively, we can see that the ground state, or in a much, so here we are going to only talk about a much overly simplified model with 4 electrons and 4 orbitals. Okay, so we consider ground state. We only consider HOMO and LUMO of the system, and ground state will be HOMO field and normal, unoccupied. However, the excited state in this picture will be, again, you have HOMO and the LUMO. One electron chain have transition from your HOMO to your LUMO. So this will be HOMO-LUMO transition here. Okay. For a dimer system, like we mentioned, now here you have a ground state of the first molecule, excited state of the first molecule, ground state of the second molecule, excited state of the second molecule. Okay? So we will consider that the system could be in a combination, compound state of these two. So both molecules can be in its ground state. That will be 1 at its ground state, and 2 at its ground state. So this is ground state 1, ground state 2. Okay. And for simplicity, usually we will just write this as the total ground state. Everything, every molecule is in its ground state. You can say you have first molecule excited, second molecule not. So I'll use another color here. So this will be actually first excited, second molecule at ground state, and first ground state, second molecule excited. So this is actually the ground state first molecule, excited state second molecule. And actually you can have both molecules excited. This will be E1. So under the Frenkel exciton model for a dimer system, you actually have 4 states. If we have n molecules, you will naturally have 2 to the n states, many of them. But in order to describe energy transfer, we concern only energy, excitation, energy transfer. We can separate these states into states with distinct energy range. What I'm saying is, if you look at the energetics of these 4 states, this state is ground state and lowest energy. Okay, those 2 are 1 exciton states because they have only 1 molecule excited. Okay, so they are called 1 exciton. And this is the 2 exciton states. If we plot the energy and those energy levels, you will say ground state is here, total ground state. Those 2 here, and this is the double excited state, 2 exciton states. Those energy gaps are optical transition energies. Those 2 energies are much smaller than that. So this spacing is very small. Those spacing are very large. And in order to have a transition between these different manifolds, you actually need interaction of your molecule with photons, with laser fields. It can only go from ground state to excited state through, or from excited state back to ground state can only be reached through interaction with photons. Okay, so without laser field, this energy cannot be provided. System will stay within each manifold. What I'm saying here is actually we can greatly reduce this problem by only focus on 1 exciton states, because for energy transfer problems that we are interested in, the most important parts are those 1 exciton states. Okay, so we focus on 1 exciton states. By doing this, we can actually write an effective Hamiltonian. So a Hamiltonian now is a matrix. It's a matrix. Matrix element here will be 1 exciton states only. So 1, 2, and 1, 2. Very often in the literature, you will see people just use first molecule excited, right? So we will write just 1, just indicate which molecule is being excited. But remind yourself that actually in this state, all other molecules also exist. Their electronic state exists in their ground states. Okay, and this will be denoted as 2. So this 1, 2 notion, or we call this side basis, because it's based on excitation on individual molecules, individual independent molecules. Now this Hamiltonian has different matrix elements. This matrix element I will call it echelon 1. This I will call it echelon 2. This echelon 1 and echelon 2 are basically the transition energy of this 1 excitation and psi 1. So this will be echelon 1. And psi 2. They are called side energies. It's the excitation energy of the molecule, the individual molecule, without the existence of other molecules. Okay, so assume that this molecule exists by itself only. Haven't interact with other molecules. And what's the electron transition energy into the excited state? That's actual diagonal of your effective Hamiltonian. Now, of course, we have off diagonal J over your Hamiltonian. And this J, by definition here, will be the electronic coupling. So this J is this J. We often call it excitonic coupling coupling between exciton states. Okay, and in this case, J is 1 and 2 of diagonal turn. More specifically, this will be the first molecule excited E1, E2, E2. And we want to evaluate this J. I want to calculate this to give you a better idea of what this is. Okay. And transfer problems. So let's see what is this. First molecule excited and second molecule on its ground state. Okay. So let's draw molecular orbitals, electronic configurations. I will draw the two molecules separately. So this will be molecule 1, molecule 2. This orbital will be the molecule 1, HOMO. This will be the molecule 2, HOMO. HOMO for molecule 2. This will be LUMO for LUMO. 2 LUMO. So just notation, okay? HOMO, HOMO, LUMO, HOMO, LUMO. Molecule 1, molecule 2. So for this configuration, first molecule is excited, so you have. Second molecule is in its ground state. So that's this. This is the electron configuration representing this quantum state, electronic state. Another electronic state, again using the same molecule 1, molecule 2, with orbitals can be written or can be displaced. This one is ground state, so in the excited state. Okay. So this one, I draw a diagram. But this MO diagram represents a configuration, electron configuration. This electron configuration corresponds to this electronic state. Okay, so this electron configuration describes this electronic state. It can be done more generally. Okay, I'm doing this in a minimum model with minimum effort, just to give you a picture. And this calculation can be actually done in a more general scheme. In that case, this electronic state can have multiple configurations. This also can have multiple configurations. But the basic principle is the same. Now each configuration actually can be written as a Slater determinant. And then we can calculate. We can actually calculate the coupling. Now I make two additional approximations. First of all, because transition from here to here, only 2 electrons changes. This electron here remains the same, no change. This electron here remains the same, no change, right? So I will neglect those 2 electrons. I will only consider 2 electrons that changes. By adding those 2 electrons, I'm not going to give you anything additional. You can just separate out. Nothing happens. Now, they have different electron spins, actually. But the problem I'm going to talk about, the spin is conserved, so I don't want to consider electron spin here. Okay, to consider electron spins, it will be more complicated, but you just need to take care of the spin wave function. Now there's no new phase in there. I will neglect electron spins. I only consider 2 electrons that actually changes. during this process. So I can write down this state as a Slater determinant. So this state, I will use 1, will be actually square root 2 of, so you see we will have 2 electrons here and here. Okay. So first electron at the lumen of the first molecule. First electron at the lumen of the first molecule. First molecule lumen at first electron. And second electron at the HOMO of the second molecule. Second electron at HOMO of the second molecule. And then you need to anti-symmetrize this wave function, okay, in order to satisfy the Pauli exclusion principle. So what I'm saying is this is a Slater determinant. So you have to exchange these two. 1L, now second electron, and 2H, now first electron. So now this wave function is anti-symmetrized, meaning you exchange 1 and 2, you have a minus sign. And the electrons are indistinguishable. Okay. Second one, this one. This first electron also. Let me highlight the 2 electron atom. I'm interested in. Okay. This 2 electrons. First electron, 1H. Second electron, 2L. Then anti-symmetrize this. H2, 1. And we want to calculate 1. Hamiltonian, 2. And this is actually an integral, right? Coefficients 1/2 integration of there were 2 electrons, so it's a tau 1, tau 2. On this side, you have complex conjugate of this 1L. And have Hamiltonian here operating on this. This is complex conjugate. Complex conjugate. Complex conjugate. It's tedious, but this algebra is simple. Not difficult at all. Now the other thing about quantum chemistry here, you learned in your quantum chemistry class here is that now both electron actually changes for all the terms. Both electron changes, right? And because of this, only the 2 electron turn in the Hamiltonian will have a non-zero, non-vanishing value in this integration. So in this double, I should say double integral. And 2 electron turn is R12. 1 over R12. R12 is the distance between electron 1 and electron 2. Okay? Since I neglect spin, I don't have to have tau here. This will be R1 and R2. Tau will be too much. So now we expand this. You have a 1, 2, 3. You have 4 turns. But you go back and check that the first 2 turns and the later 2 turns, first 2 turns and the last 2 turns, they are the same to to each other. What I'm saying here is this term and this term are the same. I will show you that here by so the first two terms is integration R1, R2, R1, R2. The first term, 1L1, 2H2, 1H1, 2L, 2. This is the first term. The last one, R1, R2. The last one is this one and this one. And if that's 1L2, 2H1, and 1H2, 2L1. It looks different originally because it's 1L1, it's 1L2. But if you recognize that 1 and 2 are electron 1 and electron 2, they are dummy variables in your integral. And actually electron 1 and electron 2, they are indistinguishable. Okay? So we can easily replace R2 and R1. We switch R2 and R1 in our integration. Okay. Oh. And here you have a 1, 2, 1. You have dummy variables in your integral. You can just switch. It's just a symbol. Means nothing. Okay. And they are the same. No. Okay. So in fact, there are only two terms in here. This 1/2 goes away. We only need to consider two terms. The first term is that term there. 1L first electron, 2H second electron, 1H first electron, 2L second electron, and then minus a second term. This term will be 1L first electron, 2H second electron, minus sign there. Minus sign here actually comes from this, and here you have a minus sign. 1 over R1, 2. Then you have 1H second electron, 2L first electron. Two terms. And I would like to rearrange these two terms a little bit by having electron 1 on one side, electron 2 on the other side. Okay? Okay. So electron 2 on the side is 1H1. So here we want 1H1. So I want to move this here. So this will be our electron 2. 2H. Just switch this. Here again, electron 2, electron 1 on the same side. So electron 1 here. This one is not that useful actually, but I'll do the same. this tells us is that there is a simple physical interpretation of these two processes, these two terms. For the first term, you can think of it as you have a electron 1 initially at the electron 1 initially at, I read it from this side up. Electron 1 initially at the lumen of molecule 1. And then it goes to HOMO of molecule 1. Electron 2, HOMO of molecule 2 goes to LUMO of molecule 2. So this process corresponds to the blue one here. This electron going down, the same electron 1. This electron going up, the blue process. Blue one here. The second one corresponds to the yellow one, okay? Electron 1 from LUMO of molecule 1 to LUMO of molecule 2. So electron goes from here to here. And this electron 2 from this HOMO to this HOMO. This is an exchange process. Whereas the first one is a Coulomb process. There's also another terminology for this. Usually this is called the Foster process or Foster mechanism. And the second one is called the Dexter process. In the Dexter process, you need to have the overlap of electron 1 and whole overlap of the LUMOs and the HOMOs. If these two molecules are separated far away from each other, the overlap of the MO will be very small. Usually you move them away apart, the interaction decays exponentially. Okay? So this is only important when those two molecules are very close to each other and they have orbital overlaps. Only important. And for normal molecular organic dyes, that will be a distance around 6 angstrom. So only important. R is the intermolecular distance. Smaller than 6 angstrom. Of course, this is just a hand waving distance. Okay, close to that. Just as a rule of thumb. However, in Coulomb mechanism, this is HOMO and LUMO of the first molecule. This is HOMO and LUMO of the second molecule. Even when they are separated far away to each other, these two molecules can actually still interact through this R12, 1 over R12 interaction. This is a Coulomb interaction. Okay. So very often we will define a quantity called transition density. Again, this is also a simplified definition. Okay. Define transition density. In normal case, this will be very small, so we are going to ignore the exchange term here. We only focus on the Coulomb term. And then if we define transition density, total transition density, because it's also related to the, when you use a photon to excite your system, you have make the electron transition from one state to excited state. It also related to this quantity. So rho n will be the transition density at the nth molecule. So I forgot to mention that what's interesting, or what's very useful property here is, now this is a property of the first molecule only. This is a property of the second molecule only. You can calculate them independent without the existence of the other molecule. And after you calculate the HOMO and LUMO of individual molecule, then you can calculate the Coulomb interaction between these two quantities. Considering that this is some sort of HOMO, LUMO, you multiply them together, you have a positive and negative part, right? Very much like some positive charge and negative charge distribution in space. So this is a bunch of charges, effective charge. They are not real charge, okay? In space. This is another bunch. And actually, if not looking here, if you take an integral of this, this will be the overlap between HOMO and LUMO of the same molecule. HOMO and LUMO are orthogonal to each other. So the density, this integration of the transition density in all space will equal to 0. Okay. So total charge is 0, but you have some sort of a charge, effective charge distribution, representing how they can interact with each other. So we define this HOMO of the nth molecule, and LUMO of the nth molecule. You multiply HOMO and LUMO, then you have the transition density. I will have R plus the R. Okay. And this electron coupling J from the nth molecule to mth molecule will be simply, or the Coulomb term approximately the Coulomb integrals. No n, sorry. Coulomb interaction between two transition densities. And if we now go a step further, you have a transition density. You have some positive, negative distribution of effective charges. And you can then calculate the dipole moment representing this charge distribution. Okay? And when you calculate this, you can actually calculate the transition dipole. So when molecules are separated far away from each other, then in electrostatics, then you then know that a bunch of charge distribution and another bunch of charge distribution, when they interact with each other at very far away, you can do a multiple expansion on them and consider charge-charge interaction, charge-dipole interaction, charge-dipole interaction, and dipole-dipole interactions, so on and so forth. Now the charge, the net charge of this system, rho n and rho m are both 0. So the first leading non-zero term is point-dipole approximations. Okay? So then it can be calculated. Point-dipole. Point-dipole approximations. I'm not going to give you the expression or the equation. It's very easy. You can look it up. But when you do this, when you do the point dipole approximation, this J and M will goes like to this. There are other factors, orientational factors, and some unit, some factors regarding the unit. But basically, inverse proportional to the R to the Q. R here is the intermolecular distance. So I don't have the plot. Molecule 1 and molecule 2, the distance between the center of the two molecules is R here. And the rate, actually rate is coupling square, so rate goes to R minus 6 power. Okay, and that's the standard Foster resonance energy transfer distance dependence that people use all the time as a measure of nanoscale distances between molecules. Okay, but I tell you this just to, you know, at least you know where it comes from. So supposedly now you know that for Frenkel model describing electron excitation energy transfer, we have a system part is the excitons, excitations, and then they can be written as, so now I write in the general form. N equals 1 to N, as shown N. And this is how we write the Hamiltonian, because this is actually a matrix element in your Hamiltonian. And N denotes the diagonal matrix elements. Diagonals are energies. I mentioned this before. And then you have a couplings. Okay. Some N, smaller N. And off diagonals are couplings. Couplings are calculated from this expression. And normally you can calculate this doing exponential calculations. There are more complicated or more sophisticated ways to calculate the couplings. It's actually available in nowadays quantum chemistry programs. So it's not that difficult. Nowadays it's not that difficult that given the molecule and you calculate the coupling between those two molecules, it can be done using quantum chemistry packages. Bass, the environment we describe as a bunch of harmonic oscillators. Here I'll use alpha as the indices. Again, I neglect the 0 point energy does not affect the dynamics of the system. As long as you take care of the energy, the reference point of your energy. And then we consider system base coupling, how this system is coupled to the base. We'll consider summation. N equals 1. N. So I consider a system with N molecules. Okay, capturing N. We need to sum over alpha also. Alpha, I didn't write the indices of alpha because this. In principle, there are infinite number of modes in this summation. And eventually, we don't want to calculate each mode. We will use spatial density to describe all the interactions. So interaction, we use so-called diagonal linear coupling model. So G and alpha is the coupling constant between the excitation on the nth molecule and the alpha phonon or best mode. Okay. Alpha. It's coupled to the diagonal psi energy.
And you have V alpha later.
This is actually a linear displacement of your mode. So displacement. This couples to diagonal energy, diagonal side energy. So this model is interpreted as you have a bunch of baths, and this bath modulates the energies of each molecule. Modulates the energy of each molecule through its position. Each bath mode at any instance of time will have a position, and depending on the position, linear. Depending on position, this molecule excitation on the n side will have a different energy. Okay. So this describes bath modes. Modulate psi energies. So linear couple to the coordinates. So each molecule have its energies budgets in time, because at any instance of time, all those modes, each mode will have a different displacement, different position. Okay. Any questions so far? As I said, this can be used to describe both excitation energy transfer problems and the electron transfer problems. The difference, there are two differences. One is the system-based coupling. For excitation energy transfer systems, molecules are usually far away to each other, so they couple to different modes. So very often, when this alpha mode is coupled to the nth molecule, it does not couple to other molecules. It's described by this general form, but usually has this property in this coupling constants. Okay, so for alpha, has only a significant value for Gn alpha. So if, for example, G1 alpha is non-zero, then other G2, G3, G whatever alpha will be zero in that case, because this mode only couples to one molecule. It does not couple to all the molecules. Okay? That's called the independent bath model. Different molecules coupled to an independent bath, they are different. However, in charge transfer problem, because you have a charge localized on your molecule, and charge whatever interactions are much stronger than exciton whatever interaction. Exciton is a charge neutral subject. Okay? So a charge coupled much longer in distance. The coupling radius is much bigger. Also, for charge transfer problems, usually the distance between those two sites are quite close to each other, a few angstrons, usually. Okay? Because they are close, so they tend to couple to the same bath. So in charge transfer model, usually this G has no n dependence. Everything coupled to the same bath. Everything coupled to the same bath. So there's some distinction there. Another is the coupling J. We just mentioned there's Coulomb mechanism for excitation energy transfer. However, for charge transfer problem, now you have a charge and electron going from one system to another system. In that case, your change of electron configuration have a different number of electrons in your donor and your acceptor. So I would say, for example, you have a system like this. Let's say charge transfer on the ground state. So you have I'll just use one electron. And this is your donor, this is your acceptor. Originally, the electron is on the donor. Okay? But then, after electron transfer, the electron goes to acceptor. This is the electron transfer case. It's a one electron problem. Okay. Only one electron transfers from one orbital to another orbital. And the coupling actually depends on, let's say this is the acceptor. Coming from one electron, donor orbital. This is one electron Hamiltonian, okay? And acceptor orbital. So it depends on the overlap. Usually this is called transfer integral. Then it depends on the overlap of these two orbitals. So this coupling is calculated differently. Again, this is also an oversimplified form, a simplest version of the electron transfer matrix element. So what I'm trying very hard to say is this is a general Hamiltonian, describe both excitation energy transfer, charge transfer, or even proton transfer, a whole array of quantum dynamical problems. However, for each problem, you might have some details that should be adjusted. The property of the bath, the nature of the couplings are the most key important parts there. Okay. Now let's keep going. So from here, and let's go back to excitation energy transfer. When you think about excitation energy transfer or electron transfer, from here one can then do two things to get your dynamics. One is assume weak system-based coupling. Weak system-based coupling. In this case, we assume this HSV is small, right? So you can do perturbation. When you do perturbation on HSV, you treat your system Hamiltonian entirely. You consider fully this. You diagonalize your system Hamiltonian. When you diagonalize your system Hamiltonian, if you have a significant J, actually the criteria is the energy gap of, if your J divided by the energy gap of your system is something not small, okay, point something, for example. Then the system, after diagonalization, the eigenstate of the system will be a superposition state of those site excitations, right? So you can have the localized excitations. The localized excitations. In this field, we often call the eigenstates of the system Hamiltonian. So you diagonalize HS for excitation energy transfer problem, then the eigenstates of HS are called excitons. This is for excitation energy transfer problem. Okay? Next, another limit. In this limit, you don't really need to consider the size of system best coupling. However, if we assume this J is large, so this is weak electronic coupling limit. Look, electronic coupling here is this J. So you do perturbation on J. Because you do perturbation on J, your so the Hamiltonian has only this diagonal electronic part, right? Meaning you work in the localized basis. In a localized basis, there is no electron coherence. So the dynamics will be some sort of incoherent dynamics. If you consider fully this time evolution driven by HS, by the system Hamiltonian, including the J here, you can have a coherent dynamics, meaning you have this quantum oscillation coming from one state to another state, because you have J here. However, if you do perturbation on this, your electronic part has only diagonal terms, then you don't have this coherent time evolution. Everything is incoherent from one side to another side. And this limit is actually the limit that you have a Foster theory or Marcus theory. Marcus theory is very famous in electron transfer. He got Nobel Prize in 1991 because of this. And the Marcus theory is doing perturbation on J. And this is the Redfield theory. In the Redfield theory, there is a very interesting range of dynamics, dynamical phenomena. So it's more interesting, and we are going to say a little bit more about this. I will upload my notes on Foster theory and Marcus theory. Actually, I don't need to upload this. You can actually find additional information on Foster theory and Marcus theory on Tokamakov's website. He have a specific chapter, have a lengthy discussion about this. I'll probably also upload my notes onto Saber, so you can read it if you are interested in. Here I'm going to only talk about this Redfield region. And the idea is that now we have the full Hamiltonian. Previously, we already derived this quantum method equation based on perturbation on HSB. Right. So the reduced density images of your electronic system, the time evolution of it can be written in this form. You have a coherent evolution driven by your system Hamiltonian, your real of the Hamiltonian. And then you have a dissipative part. We derived this previously. So we'll start from here. We'll start from here. Okay. So now it's clear that HSB, we don't know what it is. It's this, right? And this can be written as with sum over n and some collective mode notation. So this can be written as sum of n, diagonal n, q n. Okay. So qm have summation over alpha in it, and if the indices on G depends on n, so you have an n index there. Okay. And now we put an additional condition here. Assume independent path. Independent path means this Q. So this Q is actually this collective motion, collective modes, modulating the nth homophobe. And independent path approximation means we neglect the correlation of QNs. So anything we have, if we have QN, QM is 0 if n and m are on different sides. So on different sides, the correlation is 0. Independent path. Okay. So let's evaluate the kernel based on this approximation, or based on this condition, and this explicit form of system path coupling. So the kernel, what's interested is this dissipative kernel. This dissipative kernel is over path. HSB, now we can plug that in. So HSB n and then again sum over m. It's a different coordinate. We have to put it in here, and this will be now you have a time dependence in it. Let me write it more explicit. You have this potential is an operator, so you're driven by h bar I, h zero. H0 is your hs plus hv. So here I will develop HS how minus t. You have the m. I'm just plugging in the definition of this. System part of your system best coupling. And then you have a best part of your system best coupling. QM. Best part also. Exponential H bar I H bath. This is best part of T QM. Again, it's tedious, but it's not difficult. I haven't expanded the one commutator. I didn't keep it right. Okay. Tedious. Let me define this. Summation of your operators. This diagonal, side diagonal operators. Let's call this Sn. Projection operator on side N. Side N. This will be Sm. Right? And this is time evolution of Sm, so this is Sm tau minus T. This is time evolution of a best. The Q is the best mode. It contains only best operators. So of course it's only evolved by the best Hamiltonian. Just hold the best Hamiltonian. And this will be called Qn. Tau minus T. Qn. So I can put them together. But it is linear, so I'll put summation n and summation m outside. So next one, I will have summation n and m. Traceable best. Traceable best. And then we have Sn, Qn, Sm, tau minus T, Qm, tau minus T. Simplify it, having sigma T tensor will be Q double commutator. Let me do something first. First of all, you recognize that because we assume independent best. When you expand these commutators, in the end you have 4 turns, right? In each turn you have a Qn and Qm. But only when you take the thermal average, only turns that you have the same n and m survives. Otherwise, because their average correlations are 0, then it's close to 0. Meaning we don't need n and m, we need only one indices. This summation is non-zero only when n equals to m. So we'll have connect here. We keep n. Okay? And then you expand commutators. You do the average. You do the thermal average. Carefully keep the ordering of Qn and Qm. Of these two Qm. One has no time variable, one is time dependent. You carefully keep the order of it. Then you end up with, sorry, I will make a jump here because you can go back and derive all this. Okay. In the end, let's define time correlation function for the collective coordinates. Time correlation function for the collective coordinates C and P. Define time correlation function for the nth side. For the collective coordinate coupled to the nth side as Qn P Qn sum average of this. So it's called collective coordinates, just like what we calculated last time. Okay. So now you recognize this can then be evaluated through some spatial density function. All the couplings, all everything is in the spatial density. So by this definition, and we define this as a real part, prime and double prime, I think. Yeah, real part and some imaginary part. We can write down a non-Markovian form of a Redfield equation, as well as a Markovian form of a Redfield equation. As the coherent part is not changed. Part is related to this commutator Sn minus tau. Actually, to derive this, I also make a change of variables. I change. Here you have a tau minus t, right? You can change this to, you can define tau prime, I think t minus tau. Change variables to tau prime. And tau prime is a dynamic variable, so we can call it tau. That tau will be that tau. It's all in the lecture notes. So we collect the real part, and later for the time correlation, we recognize there is a real part and imaginary part. And we collect the real part and the imaginary part separately. You reach the equation. Sn minus tau, t, double commutator, then plus I, double n, tau. Plus. So this plus here is the anti-commutator. Commutator, you have a AV minus VA. Here you have a AV plus VA, or just a notation. So first one is anti-commutator. Then you have a normal commutator. That's it. Now, if your dynamical variable, your time actually is already exceeds your best relaxation time. So if your time is much greater than tau v is the best relaxation time in which the time correlation function already decays to 0. Okay, so tau v for tau greater than tau v. The time correlation function already decays to 0. So this is called the best correlation the case. The time coefficient already decays to 0, so this integration from 0 to t can be extended to from 0 to infinite, because anything beyond t is already effectively 0, 0, 0. Understand what I'm saying here? Okay. And by doing this, we reach a new equation. That has a kernel that does not explicitly depend on the, so the best part now is no longer depends on, here it goes to infinite. And now because this inference has no time dependence in this is Markovian or Markovian Redfield equation. This is the matrix form of your Redfield equation, or Markovian quantum master equation. When Redfield first proposed his equation, he explicitly write the time evolution of density matrices in the eigenbasis of the electronic, Hamiltonian, or your sister Hamiltonian. So in that case, you diagonalize HS, so you have HS alpha is H alpha alpha. If you already have the matrix, regardless of the dimensionality of your matrix, you have n equals to 100, 1000, whatever. You construct a matrix, use a numerical program to diagonalize your matrix. Very easy to do. Okay. In MATLAB, it takes no time to get this. And with this, you also have the coefficient that translates the side basis into your eigenbasis. So for each alpha, exciton state is a linear combination of a side localized, side excited states. You know those coefficients. So given HS, it's easy to get the spectrum coefficients. So in this case, this S alpha beta, by definition, will be alpha S alpha beta for Sn alpha beta. By definition, alpha Sn beta will be alpha n beta. And simply the coefficient, this is complex conjugate of the coefficient of the nth side in the alpha's eigenstate, exciton state. Okay, it's very long in the description, but its meaning should be simple to you. And this is coefficient of n in beta, in the eigenstates. So this is the kind of coefficient of that. Okay. So we can explicitly write that it's complicated. Still, you should check in the lecture note we want to explicitly write this sigma dot alpha beta t as alpha beta. And you plug in this into here. You have those commutators on Sn, but then you can insert identities. Identity, you can insert sum over. Sum over alpha, sum over beta. Standard procedure, you insert identities to expand everything in the exciton basis. So you can write down the density matrix elements, evolution of density matrix elements in the exciton basis as a function of those base parameters, C calculated functions, and the density matrix elements in the exciton basis. Okay. Let me see. Should I copy this? No, I don't want to copy. This is just too long, a waste of time. Now, the key thing is when you do this expansion, and in the end, your equation of motion can be written as minus I. Now you have omega alpha minus omega beta. This comes from the coherent term. This part. You take alpha beta eigenfunctions of Hs, so you have the energy there. So sigma alpha beta E plus. Now the dissipative kernel part can then be written as a Redfield tensor term. Gamma delta. Alpha, beta, gamma, delta, sigma, gamma, delta, t. And this is called Redfield tensor. This is a very general form because if you just read it, it means that to have a time evolution, time derivative of the density matrix element alpha beta, you have a coherent term that's driven by the zeroth order, the system part of the Hamiltonian. It's just nature that you have this. And then the best effect, the dissipative kernel then became this is a tensor because you have a alpha, beta, gamma, delta, 4 indices. It's a rank 4 tensor. Okay? And this tensor tells you that, well, to have some derivative of alpha beta, you need to consider some coefficient times all other gamma delta goes from 1 to n, all the other density matrix elements. So this tensor just transformed. This is an array with n to the square elements. This is another array with n to the square elements. And this is a matrix. I write it like this. You think this is some sort of matrix with n squared times n squared elements. It's a very general form with linear transformations from one array in the Liouville space or matrix in normal Hilbert space to another array or matrix. Right? Just a very simple form. And in this form, we actually can have some interesting or some physics. We can relate Redfield tensor to different physics. Redfield tensor describes population transfer. Population transfer means you have a population on one exciton state relaxed into population at another exciton state. So you can have a population transfer. Population transfer will be something like this. Your Redfield tensor. And this will be going from, you see, here is rho VV. Rho VV will be population at B, state B, right? I didn't use alpha or beta, just not confused with these indices. And then it goes to rho alpha beta. Now alpha beta is AA, so it's rho AA. It became the change in the population of state A. So that's a population transfer term. Tells you the transfer transition rate constant from B to A. So this tells you a transition rate constant. It's a rate constant. A rate constant. You also have a dephasing. For terms like R, Redfield tensor AB, AB, and A does not equals to B, does not equal to B. In this term, you have here AB and here AB. They are coherences. Coherences can decay in time, so this constant between it is the dephasing rate. Dephasing. Sigma AB is an off-diagonal density matrix element with coherence. This coherence can decay by determined by this constant. Naturally, this will be some negative value. Then you can have a coherence dynamics. You have coherence to dynamic population. This population to coherence transfer. Since that on one side you have a coherence AB, AA, or AA, AB. You have a coherence transfer. Going from one coherence to another coherence. Because those terms, we have an integral here. Integral here. So in this integration, if this turns in here, especially those time evolution depending on S, if they are stationary, meaning the time evolution sort of cancels out this phase factor in there, okay? Or if they change slowly, then you have when you do the integration, you have a large value, significant value. However, if in here you have those terms that the phase cannot cancel out each other, they change rapidly. When you do the integration, this term changes from positive value and negative value rapidly. In the end, the integration of everything, because positive, negative, they cancel out each other. The value will be small. Okay, so for this integral to have a significant value, there's some sort of a stationary condition in there that must be satisfied. For population transfer and the dephasing terms, this condition is satisfied. However, for this coherent dynamics, relation to coherence transfer or coherence transfer terms, normally, in general, the stationary condition is not satisfied, so they are much smaller. So normally they are much. And very often one applied so-called secular approximation. Secular means it's the rule of God, so it's something you must do or what. So when one applies secular approximation only in these two are considered. Those are called non-secular terms. They are normally ignored. Okay, so rule one is secular approximation. Secular approximations are normally applied in Redfield equation, because Redfield equation without secular approximation very often gives you trouble. Easily violates the positivity condition of a reduced density matrix and makes the results unusable, useless. However, very often when you apply secular approximation, you get reasonable, not bad results. The other thing is, of course, the Redfield equation is only valid when the system-based couplings are small. It's the weak system-based coupling limit. The Foster or Marcus theory works in the weak electronic coupling limits. But very often in materials, in biological systems, the reality is the system could be in between, in a so-called intermediate coupling limit. In that case, both Redfield equation and the Foster equation, both of them just do not work. You need a more general method. And that kind of method do exist, but they are more complicated than this, and it's not the topic that I'm going to cover in this lecture series. Finally, just the last part of this. It essentially will be a good exercise to do the expansion and actually derive an expression of this Redfield tensor. It's in the lecture note, but you can work out. You can work out. And this kind of stuff, if you never actually write it down and work on the algebra, you don't really learn anything. Okay. Just by me copy my lecture note expression on the blackboard is not very useful for you, actually. Okay. So let me do the last thing is, we can actually calculate the population transfer rate from one state, eigenstate B to another eigenstate A. Okay. And this can be calculated easily as this expression. Actually, you can append exactly the same expression from Fermi-Gordon rule. This is the Fermi-Gordon rule expression. Although the derivation is quite different from what we did in the first-order time-dependent perturbation theory to obtain the Fermi-Gordon rule, but the end results are the same. It happens all the time in quantum dynamics. So after you calculated everything, we will have reached something like this. And then you should recognize that this part here is some sort of a Fourier transform of this function, your time function. It's a one-sided Fourier transform. Okay, but as long as we keep the real imaginary, so the even odd correctly, this can be rewritten into a full Fourier transform. So another exercise, you can go to check this equals to square. Yeah, there's a square here. Sorry. Some of n, c, and a square. Real part of I'll write this first. Minus infinite to infinite. Extend this to minus infinite. And I have only c here, a single c power here, because I assume identical. There were many molecules. Each molecule coupled to a different mass. Okay, so Cn represents the system-based coupling of the n molecule to its base. But then I further assume that all the bases has the same spatial density. They are different bases, but they are identical bases. Okay, so this identical independent base model is actually quite commonly employed in the excitation energy transfer problem. And this is a Fourier transform. Real part of Fourier transform over the time covariance function. And this can be calculated from your spatial density that we defined last time. Fourier transform this and detect the frequency component and the energy gap of these two states. This expression tells us that the transition rate from one exciton state to another exciton state depends on two things. First part here is CNA squared. What is this? This is the population of the AA is the exciton state, eigenstate. Of this eigenstate, population of A on psi n, coefficient squared population. The likelihood, the probability of finding psi n at A state, right? This is population of B at the nth site. And this is site population multiplied by each other. So this is some sort of population overlap. Okay? So this is overlap factor. LAP, overlap factor. Okay. A and B. So A and B are delocalized eigenstates. However, to have energy transfer between them, energy realization between them effectively, if efficiently, quickly, you need to have a significant site population overlap. They must have a distribution on the same site. The reason for this is actually simple because they must couple to on the same site, then they can couple to the same vibrational mode. They must exchange energy through the same vibrational modes. Okay, so this actually comes from the uncorrelated or independent Bass approximation assumption. So the spatial distribution of the excitation excitons when they are close to each other having a big overlap factor, then the transition will be fast. If they are separated in space, then you don't expect them to have a significant relaxation rate between them. And this, what is this? Time correlation function of your Bass has, this is determined by the coupling strength times the effective density of states, right? And this is Fourier transform of that, so it has some more factors in it, but the essence is still, do you have a vibration or Bass state at this energy to take this energy away, or to provide this energy? If the transition is uphill, you need to take energy from the environment, from the Bass. If you are doing a relaxation, going from high energy state to low energy state, you need to dump that energy into the environment, into the Bass. And you need the Bass to have a mode in that frequency to take this energy. Okay? So this is actually a energy conservation term. Energy conservation here means the energy difference of your electronic state must be dumped to the environment. Energy conservation. And this is actually describe the electronic coupling factor, or some sort of coupling strength. Coupling strength, energy conservation. Again, the essence of Fermi's golden rule. Okay. I don't have time to prove a very important relationship. So I will write it down and leave it to you as an exercise. And it's actually simple. Oh no, actually I can prove it. So now I have a KB to A. So now I can write KA to B. Then we'll just switch the things, okay? So 1 over H bar square. And now real part of this hyper is frequency domain time correlation function, but now you have omega A minus omega B. So the ratio between them from B to A divided by A to B. The prefactors are all the same, so you have this only difference in your time correlation function, Fourier transform your time correlation functions. In the last lecture, I uploaded a note about this detailed balance condition of time correlation functions onto the SAVE app. So if you go to SAVE app, download the PDF file, read the content, it will tell you that any time correlation function, Fourier transform of a time correlation function, the C omega and the C minus omega will always differ by a ratio of a Boltzmann factor. Okay, so So this is by the nature of a time current function. It will be exponential with rate, delta h bar, omega b minus omega a. So this means the downhill rate and the uphill rate are always differ by a ratio of a Boltzmann factor. And downhill, when omega b is larger than omega a, this is positive, this is negative. This is positive. So downhill is always faster than the uphill ones. This satisfies the detailed balance. Condition. It's detailed balance because now in all the states you have all the transitions, okay, forward and backwards, and each pair satisfies this Boltzmann factor. This is called detailed balance. Okay, because each pair satisfies the Boltzmann factor, then at very long time when the system reaches the equilibrium, this will guarantee the Boltzmann distribution of the system. Okay? Because when you write down the mass state equation, you have the rate difference differ by this Boltzmann factor. If you have the population differ by another Boltzmann factor, just the negative of this. High energy state has lower population than the low energy state. It cancels out. Right? It guarantees everything is one now. Guarantees the equilibrium within your system. Okay? It guarantees that all the backward forward reach equilibrium and this Boltzmann distribution of populations. So this enforces Boltzmann distribution. Or the canonical distribution, canonical ensemble of your system. Okay. But unfortunately, this is only true when you have a secular approximation. Okay, because when you have a secular approximation, your population transfer are decoupled from them, right? So this backward, when you consider this backward forward transition, you only consider within populations. Nothing from the coherence will be involved. However, if you consider the full Redfield equation, when you consider those two terms, and this breaks down, right? Right? Okay. So when you consider these two terms, the population satisfies the detailed balance, but the total equation of motion, because now those terms do not satisfy detailed balance, they will destroy the Boltzmann distribution in your stationary solution. Okay. Okay. So for normally secular Redfield equation guarantees detailed balance and have good behavior in your time evolution. However, if you consider a full Redfield equation, detailed balance can be broken, and even the positivity of the decimations could be violated. Okay. And that's actually a serious problem in the application of Redfield equation. Okay. Okay, I think that's all I want to say. So I skipped some details, but hopefully the basic idea is still there. And some of those you should go back and derive the equation by yourself. That's the only way that you can learn this kind of stuff. Those algebra are not that difficult, but it's tedious. And some details can only be learned if you actually go through the derivation. Okay? Questions? Okay, if not, that's it.